Okay, we just have a couple more examples to work through. We're going to look at this sequence where k is a constant. So just think of this as, some number, 2 or 3 or something. Don't think of it as a variable. So when we look to see what happens as n goes to infinity, then we have this part right here. We have some number dividing by something very large. So this portion is going to 0. So the base is going to 1. And then we're raising it to a very large exponent, so approaching infinity. So we get something of the form 1 to the infinity. So this is indeterminate form, which we know it's indeterminate form because let's think about it this way. If you had some real number raised to a very large power, that would be going to some really large number. Whereas if you had we had 1 raised to some real number, then that would be 1. So these two things are different. So that's indeterminate form. We want to try to apply L'Hopital's rule. Now, L'Hopital's rule, as we know, is something for quotients, and we don't have a quotient. We have something of exponential form. So we're going to need to use our natural log trick in order to get that exponent down. So we set this equal to y, and the goal will be to solve for y. So we take the natural log of both sides. And remember that we can interchange the order of the natural log and the limit. So this is the limit as n goes to infinity of the natural log of 1 plus k over n to the nth. And we get to use logarithm properties now to pull this n down. So we have the natural log of y is equal to the limit as n goes to infinity of n times the natural log of 1 plus k over n. So using this logarithm property has successfully turned our exponent into a multiplication. And now to turn our multiplication into a division, we have to take the reciprocal of one of these things. So looking ahead, knowing when I'll be using L'Hopital's rule and taking derivatives of these, I'd much rather take the reciprocal of this portion. So I'm going to write this as the limit as n goes to infinity. I'm going to leave the natural log of 1 plus k over n alone. And I'm going to divide it by the reciprocal of n. So divide it by 1 over n. So note that this is equivalent, right? We're multiplying these two numbers versus dividing these two numbers. These are exactly equal. I haven't done anything fancy, just taken advantage of the fact that multiplication can be written as division. Okay, so I finally wrote it as a quotient. That's good, right? So the whole point is we wrote it as a quotient, which means we'll be able to apply L'Hopital's rule. Let's just double check that we're still of indeterminate form, which it should be at this point. So if we do direct substitution, this part goes to 0. So we've got natural log of 1, which is 0, over 1 divided by infinity, so that's 0. So this is of indeterminate form, and we can apply L'Hopital's rule. Okay, I think I'm going to have to steal some of this space here from this one. So we have the natural log of y is equal to, applying L'Hopital's rule, we want to take the derivative of the numerator. So that's 1 over 1 plus k over n times the derivative of 1 plus k over n. Now the derivative of 1 is 0, and the derivative of k over n, the way you want to be thinking about that is that's just some coefficient times n to the negative 1 power. So its derivative is just negative k n to the negative 2. That's the derivative of the numerator. And then the derivative of the denominator, again, this is just n to the negative 1. So the denominator's derivative is negative n to the negative 2. So we get the factor of the negative n to the negative 2. Those cancel. And so we're just left with the natural log of y is equal to the limit as n goes to infinity of k is left, right? That stays in the numerator, over 1 plus k over n. Okay, so we've applied L'Hopital's rule. Now as we take n going towards infinity, this portion right here is going to go to 0, and so we're just left with k. So natural log of y is equal to k. Solving for y, e to the natural log of y is equal to e to the k, and so y is equal to e to the k. So we would say that this sequence a sub n converges to e to the k. And notice that we did this problem in general in terms of k. So if I were to replace this with like a 2, then we know that the sequence would converge to e squared. Or if I change it to a 3, it converges to e cubed, etc. So we've done it in general. Okay, so we have the next problem, number 24. I'm going to erase some of this stuff right here. now that I've made a mess. So again, we're looking at the sequence. We want to see, does the sequence converge or not? So we're going to take the limit as n goes to infinity. Now, while I'm erasing, I'll leave that there. That's fine. Okay, so we want to take the limit as n goes to infinity of sine of n over n. Notice that what's happening to sine of n? Well, sine is a periodic function. It just oscillates back and forth between -1 and 1, right? Some value in between -1 and 1. So it's going somewhere between -1 and 1, so that's a number, but I'm still dividing it by something approaching infinity. So this is something between -1 and 1. So I've got some constant between -1 and 1, but I'm dividing by something very large. So this is just going to go to 0. So we didn't need that much room to say that this sequence converges to 0. And the last exercise here in the notes we've already done. So that was sort of silly. It was a repeat question, right? We already did this one. We saw it as the nth root of n, but we did that above. Okay, so you're now ready for homework 1. This might be an old packet because we're going to be looking for you to be doing it on WebAssign. So look for now officially your WebAssign series homework number 1 will be there. Okay, and please email me if you have any questions on this stuff.